Good morning, Algebra 2, or good afternoon, but I think it's morning for most of you. Anyways, we're jumping into our next unit on a bunch of things: polynomials, radicals, and something called complex numbers. Eek! Don't worry, we're not going to get to those for a little while. But today's lesson is going to be pretty much a big review of Algebra 1, going over some basic operations, adding, subtracting, and multiplying these things called polynomials. But before we get to a polynomial, we have to start with the more basic monomial. Now, you might recognize this prefix mono. It actually means one. And so a monomial is just a number, a single variable, or the product of a number and a variable, which just means like a whole combo, right? So here's some examples down below. 4, that's a monomial, it's a single term. Z, that's a variable, that's just a single term. If you combine them, 5x, that's one term, that's a monomial. You can even have multiple variables, 8x squared, y to the ninth. These are all examples of monomials because they are a single term. You're only going to get multiple terms if you start adding and subtracting different groups of these together. So if I had x plus y, well, this plus sign is now combining two different monomials. So this would be one monomial. This is a second monomial, which means the whole thing is not a monomial if you're adding, all right, or subtracting. So just those 4 examples up there. And again, the easiest way to determine it, if it's a monomial, is just make sure you're not adding or subtracting anything else from it. And hey, that's a monomial. And terms that I know you already know, but I just want to reinforce it. So if you hear these terms enough, you're going to definitely have them locked down. So a constant, that's what you call any term or any monomial that doesn't have a variable. So it's just a number by itself, like 3 or negative 16. A coefficient, well, that's also a number, but this specifically is a number in front of a variable, okay, or in front of the rest of a monomial. If there are multiple, variables in the term or in that monomial, then the number in front is the coefficient. So I'll be using those terms a lot, but you've already been hearing me use those, so you should be good with that. Now, these monomials have very particular properties. And so I just want to review all these with you to make sure you know what's going on. So x to the second times x to the fifth. Now right here, I'm multiplying two different x variables. Now x is the same thing, and it's just got different exponents. And if you recall, an exponent just means you're multiplying that base multiple times. Like x to the second right here, that means I'm multiplying two x's together. So it's like 1x times another x. And then x to the fifth means I'm multiplying 5 x's. So 1, 2, 3, 4, 5. And if I'm multiplying both of these together, x to the second and x to the fifth, well, how many x's altogether are being multiplied? Well, if you just count them up, you'll see that there are 7. Awesome. Okay, but there's got to be an easier way to do that than writing them all out. And yes, there is. Whenever you are multiplying the same base multiple times, to combine their exponents, you simply add them up. So x to the 2 plus 5 just equals x to the 7th. Now on that second monomial down here, that's x squared to the 5th. What this really means is I've got 5 x squared. So it's like x squared, that's 1, times another x squared, that's 2 of them, 3 of them, 4 of them, 5 of them, right? I've got x to the second 5 times. So how many x's are all together? Well, in essence, whenever you've got x to the second to the 5th, instead of adding those exponents, because there's only one base, see how like x is only written one time, where in the previous example, the x's each were written a separate time. So when there's only one base, you're going to actually multiply those exponents 2 times 5, which gives us x to the 10th. Students always mix these up, and the best way that I can kind of guide you or give you a trick to remember it by is by thinking about this parenthesis right here, and this 5 is outside of the parenthesis. And whenever you've got something outside of a parenthesis and you like distribute it into anything inside the parentheses, you always multiply, right? Like distribution is multiplication. So that same rule would apply here. When you've got an exponent outside, you distribute it into every other exponent inside, and you just multiply them. So x to the 2 to the 5th is actually x to the 10th. And finally, we've got some division down here. And so in this case, when you're dividing exponents, I mean, if you want to think about it, hey, what's really going on here? Well, if I've got 5 x's on top, 1, 2, 3, 4, 5, and I've got only 2 x's on the bottom, you know how whenever you have a fraction and you have the same thing on the top and the bottom, you can cross them off? Well, check this out. 1x on top, 1x on bottom, gone. Another x on top, another x on bottom, gone. What are we left with? Well, there are 3 x's on top. So this is x to the 3rd. Now, what's really going on here with this operation? I mean, if you want the little shortcut, basically whenever you're dividing the same base, you just subtract the exponents. So x to the 5 minus 2 gives you x to the 3rd. Hopefully you recall these rules from way back in Algebra 1. There's some other ones we need to be familiar with. And so let's talk about distributing first. So whenever you've got an exponent outside of some parentheses of a monomial, you have to think, all right, so this is all being squared, but what inside is actually being squared? And you have to look at every single base. Now, when I say base, I'm talking about, like y is the base and 4 would be what we call an exponent. So when I say base, I mean like that main number on the bottom. So y is a base. X is also a separate base from y. It's got its own exponent of a 3. And here's the tricky part. This 2 is a base as well, right? That's actually 2 raised to the first power, but we don't always, write that exponent of a 1. There's no need to. So inside the parentheses, there are 3 bases. And this 2 that's outside of the parentheses is going to distribute to every one of those exponents. Now make sure you're only multiplying the exponents together. Don't multiply that 2 like times the base itself. So these 3 different bases inside the parentheses, the 2, the x, and the y, it's going to be 2 to the, well, it did have a 1 for an exponent, and when we distribute, we multiply, so 1 times 2 is 2. The next term is x. Now the x already has a 3, so I'm going to multiply it with that 2 that's being distributed. 3 times 2 is 6. And then the y, that's our last base. It has an exponent of a 4. And so when we distribute the 2 inside, it's going to be 4 times 2 to give us 8. Last thing we would do is any bases that are numbers that are like integers to an exponent, like this 2 to the 2nd right here, we can actually multiply that out. We know that 2 squared is 4. We always want to do that. We don't want to leave an exponent hanging outside of a number if you can actually calculate what that value is. Then the x to the 6th, y to the 8th wouldn't change at all. So that's that first one. Now that second one on the bottom, we've got this 3 of an exponent outside the parentheses, and it has to be distributed inside the parentheses to every base, regardless of whether that base is in the numerator or in the denominator. So how many bases do we have altogether inside? Well, this 3 is a base, the y is a base, and the x is a base. So all 3 of those bases are going to get this exponent of a 3 distributed to them. Now, those bases aren't going to switch their positions or anything. They're going to stay put. But now this 3 that's in the numerator is going to become 3 to the 3rd power. The y in the numerator will become y to the 3rd power. And down on the bottom in the denominator, x to the 6th, well, I have to multiply the exponents together, and 6 times 3 is 18. Our last step is going to be to multiply out that leading term, that number, because 3 to the 3rd power, we can calculate that. That's actually 27. So we get 27 y cubed over x to the 18th. All right, so that's distributing exponents. So much fun. Ooh, special cases. X to the 0. A lot of times kids want to say, oh, that's just a 0. Not quite. As it turns out, anything to the 0 power equals 1. I know, it's crazy. Totally bananas. Now, this second one, x to the negative 2, well, we can't have negative exponents. All a negative exponent does is it moves the entire term, like the base and the exponent. So not the term, but the base with that exponent. It's going to flip the side of the fraction that it's on. So what I mean is we can think of this x to the negative 2 being over 1, right? You can always write anything over 1, and it doesn't change its value. Right now, that x to the negative 2 is in the numerator position. But because that x has a negative exponent, we want to flip it to the other side of the fraction. So I'm going to flip it down to the bottom. And when you do that, that exponent of a negative 2 becomes a positive 2. Da, 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 da. Now we're happy because we don't have a negative exponent, because negative exponents are crazy. And if there's nothing else on top in the numerator, you always just put a 1 there as like a placeholder. Okie dokie. All right, go ahead and try this one on your own. And you can pause the video if you want, work it out, and then see if you get what I get. Here's what I would do. I look at inside the parentheses how many bases there are. 1, 2, 3 of them. And each base is going to get this exponent of a 4. And so I think about distributing that 4 to every base. When I do that, I'm going to get 2 to the 4th power. X to the, well, it already has a 3 for an exponent, so I've got to multiply those together and get 12. And then y to the 4th. Last thing is to multiply out that leading coefficient since it's an actual number. 2 to the 4th power, that's 2 times 2 times 2 times 2. That's a lot of 2's. Ends up being 16. The variables stay the same, x to the 12th, y to the 4th. Hopefully you got that right. Example 2. All right, go ahead, write this down. Go ahead and pause the video. Try to work it out for yourself and see if you get what I get. So right here, I've got a couple different terms, some coefficients, and that same variable twice. But the key thing is there are parentheses. And just like good old PEMDAS tells us, you've always got to get rid of parentheses first. So I'm going to distribute this 2 just inside the parentheses. Now it's got to go to every base. So don't just write 2j squared, because the 2 and the j are their own separate bases. They each can have this exponent of a 2. So when we expand this, first off, that first term, 5j to the negative 6, we can just leave that where it is. But now the second part is going to be 2 to the second, this is being multiplied, 2 to the second, j to the second. Okay. Well, we want to combine like terms. And the 5 and that j to the negative 6, they're just being multiplied. In fact, everything is being multiplied. And multiplication with variables or integers is commutative, unlike matrices. So we can switch the order all around, meaning I could make this 5 times the 2 squared times j to the negative 6 times j squared. We're just going to multiply the like bases together. Now in this case, up front here, you've got 5 times 2 squared. Well, that's the same as 5 times 4, because 2 squared is 4. When I multiply those together, we just get 20. Now, what about the j's? Okay, so I've got the same base being multiplied together, j, and the rule was when you're multiplying the same base, you add the exponents. So it's a negative 6 plus 2, which equals a negative 4. So this term is going to be 20j to the negative 4. Well, it looks pretty good. We've combined our coefficients, we've combined our variables, but we're not quite done because there's this negative exponent. And remember, we don't like negative exponents. They're evil. So what we need to do, if you recall from that earlier example, is if you ever have a negative exponent, you simply move the base of that negative exponent onto the other side of a fraction. So we think of this as being 20j to the negative 4 over 1. Okay? And right now, that 20j to the negative 4 is in the numerator. We don't want it in the numerator because it's got that negative exponent. But here's the hardest part for students to comprehend, I guess. Oftentimes, students will move the 20 down to the denominator as well. However, the 20 and the j are separate, right? That 20 is its own base. Technically, that's 20 raised to the first power. And so that 20, it doesn't have a negative exponent. It has a positive exponent, right? A positive 1. So the 20 is going to stay put in the numerator. Only the j has a negative exponent. So the j is going to move to the denominator, and it's going to change its negative 4 exponent to a positive 4 exponent. And this is our final answer. Moving on. Ooh. All right, we got a lot of stuff going on here. A bunch of different monomials all being multiplied together. First rule is to always get rid of parentheses. Right here, we've got these parentheses all being squared. So I'm going to distribute that 2 inside the parentheses to each one of those bases. Now this first term, 5pn to the 5th, is fine. It can stay put. It's being multiplied by this middle term, which is now going to be 3 to the 2nd. P to the 6 times 2 is 12, and then n to the 2nd. And then at the end, we've got this times negative 2n. So I'm just going to put negative 2 in parentheses just because it's being multiplied. If I just wrote negative 2, people might think you're subtracting 2, and that's clearly not the case. So we've got a bunch of coefficients, a bunch of p's, a bunch of n's, and so we're going to combine everything. First off, I'm going to take 5 times 3 squared, and we know 3 squared is actually 9, and a negative 2. So those are all of our coefficients. We want to multiply them all together, right? So it's, let me do this over to the side here. So I got 5 times 9 times parentheses negative 2, just so we know that we're not subtracting 2. Well, 5 times 9 is 45. And then 45 times negative 2 is negative 90. So negative 90 is our new coefficient, negative 90. I should have put it on purple. You know, I kind of got this theme going, this color coding. There we go, much better. All right, now let's multiply the p's and the n's together. So right here, I've got a p to the, I guess that'd be the first power, and a p to the 12th power, and that's it. When you're multiplying the same base, you simply add the exponents. Well, 1 plus 12 is 13. All right, last step. I'm going to multiply all the n's together. That's n to the 5th times n to the 2nd times n to the, nothing there, put a 1. So altogether, we have n to the 5 plus 12. 5 plus 12 is 17. 17 plus 1 is 18. So negative 90, p to the 13th, n to the 18th would be our final answer. I guess technically we could put the variables in alphabetical order. Sometimes that's preferred. I'm not going to get too stingy upon that. I'm fine with you leaving the variables in any order, but it should be the coefficient first, and n comes before p, so it should be n to the 18th, p to the 13th for the true, proper final answer. Hopefully you got those right. Ooh, man, why do these keep on getting so tricky? Don't worry, it's not that bad. I know there's like a billion terms in this one, but I'm going to show you how to make this nice and easy. Trust me, I've got a really cool method for simplifying these big monomial fractions. What you want to do is think about grouping off each like base. Now, the coefficients are kind of their own base. Even though 4 and 12 are different numbers, they're both numbers. They're both coefficients, so I always group them together. Then you've got the x's, and you got the y's, and then you got the z's. And you're basically just going to simplify each of those like vertical groupings together. So first, look at those coefficients, the 4 over 12. if you think of that as just a fraction, hey, if I said 4 over 12, can you simplify that for me? Sure. 4 and 12 are both divisible by 4. And so you divide the numerator and denominator by 4, and you'd get 1 over 3. So that's what we would do to simplify this first grouping. You have 1 over 3, 1/3. Cool. Now go to the second grouping of the x's. And all we're going to do is, since I've got some x's on top and some x's on bottom, I'm going to look at their exponents. And here's the questions that you need to ask yourself. You have two questions to determine where does the x go, because we're going to combine it. We don't need x's on top and x's on the bottom. So my first question to you is, where are there more x's, on the top or on the bottom? And so you're really looking at just the exponents. Which number is bigger, a -4 or a +9? Obviously, 9 is a bigger number. Since that's the bigger number, that's where there are more x's. So there are more x's in the denominator. So I know that my final simplified fraction is going to have x in the denominator. But now we need to determine what its exponent is going to be. And to answer that one, you simply say, okay, so we know there are more x's in the bottom, but how many more x's are in the bottom? Basically, how much bigger is 9 from a -4? And you can really just subtract those, right? Take a 9 and subtract a -4. Yes, it's a double negative. And you get 13, right? Because 9 is actually 13 numbers greater than a -4. So since there are 13 more x's in the bottom than on the top, back in our simplified fraction, we're going to say this is x to the 13th in the denominator. Do the same thing with the y's. Okay, where are there more y's, on the top or on the bottom? Well, there are more y's on the top, so that's where I'm going to put y in my final answer. And how many more y's are up top? Well, I'm comparing a 2 to a 1. And that's 1 bigger. There's 1 more y up top than in the bottom. Perfect. So we have y to the 4 up top. Last, I'm comparing the z's. Z to the first compared to z to the third. Where are there more z's, top or bottom? Well, there are more z's on the bottom because 3 is bigger than 1. How many more z's are on the bottom? Well, that would be 2 because you're comparing a 3 to a 1, and 3 is 2 more than 1. Okay, so we've gone through each and every grouping. Final step is just to simplify everything. For example, in the numerator, I don't need to write this 1 of a coefficient or this 1 for an exponent, so I'm just going to write y over 3x to the 13th z squared. And that's your final simplified answer. Dun, 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 dun. You're doing great so far, everybody. Keep up the good work. What? This is crazy. Yeah, it kind of is, but it's not too bad. Remember, I always tell you to make sure you understand the difference between a difficult problem and just a really long problem that you might have. And so this might be a longer type of problem than you're used to. There's a lot of steps, but they're all simple in themselves. They're not difficult. So we've got this exponent outside the parentheses, and it's got to distribute inside to every single base inside the parentheses, in the numerator and in the denominator. So that's 1, 2, 3, 4, 5, 6, 7 bases, and they're all going to get a 4, this 4 that's outside for its exponent. Unless they already have an exponent, then you multiply them. All right, so let's see what we got. First, you've got that 3 to the 4th. A to the, well, it already has a 4, so we multiply those exponents and get 16. The B already has an exponent of a 3. Multiply those and you get 12. C to the 4th, it didn't have an exponent, so it just gets that 4. In the denominator, we're going to have A to the 4th, B to the 5 times 4 is 20, and C to the 4th. Wow, that was so difficult. No, it wasn't. This is easy. Right now, this problem looks just like that previous one that we had, right? I can separate all the different bases like this, nice and easy. Starting things off, we've got the coefficient 3 to the 4th. That's 3 times 3 times 3 times 3, which is 81. Now go to the a's. Where are there more a's, on top or bottom? Up top. How many more a's are up top? 12, right? Because 16 is 12 more than 4. Now go to the b's. Where are there more b's, top or bottom? Well, there are more b's on the bottom in the denominator, so I'm going to put b in my denominator of my simplified answer. And how many more b's are on the bottom? Well, that would just be 8. You're comparing a 20 to a 12, and that's 8 bigger on the bottom, 8 more on the bottom. Finally, you've got the c's, c to the fourth over c to the fourth. Where are there more c's? Well, nowhere. It's the same amount. And anything divided by itself just cancels. So the c isn't even in our final solution. And there you go. Simplified. Last one. Ready, go. Are you done yet? I hope so. See this exponent? A 0. Anything raised to the 0 power equals a big fat 1. So this whole thing, this whole crazy expression here, since all of it is being raised to the 0 power, that's just a 1. Da 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 da. And guess what? You have finished your lesson's first half. Whoa, so close, right? Those were all monomials, single terms, and I was just kind of reviewing those exponent rules. But now we get to the real part of the lesson, which is polynomials. Ooh, fancy. This prefix poly means many. Although the wording is a bit tricky because a polynomial could technically be just a monomial in math. It's weird, I know. If it's one term, why is it a mono? Typically, it's going to be a sum of monomials, meaning you're going to be adding them together or subtracting them, right? Like 2x squared plus 3x minus 5 would be a polynomial. Now, when you're adding these up, your polynomial is made up of all these smaller monomials, which we generally call terms. I'm sure you've heard that, right? Hey, there's 3 terms in this polynomial. The number of terms that a polynomial has gives it a special name. For example, a binomial has 2 terms, since the prefix bi means 2. A trinomial has 3 terms, because the prefix tri means 3. And there's one more term, not a polynomial term, but like a vocabulary term that you should know, and that is the word degree. And the degree of a polynomial, very simple, it's the largest exponent. So if I had a polynomial that was like 3x squared minus x to the 6th plus 3002x to the 3rd, well, the degree of this polynomial would be 6 because it's the biggest exponent. All right, I just have some practice problems for you with these polynomials, with those basic operations. Again, it should be stuff you're mostly familiar with. So first off, combining like terms, right? This is a gigantic polynomial. There's 1, 2, 3, 4, 5, 6. There are 7 terms in this polynomial, but we can simplify it by just combining like terms. Now, a like term is the same variable and the same exponent. So looking at this first term, this is just an x by itself, or x to the first power, you might think of it. Are there any other just plain old x's anywhere in this problem? Sure is. If I have 3 x's here, and I add 8 x's over there, well, how many x's do we have altogether? Well, we have 11 x's. Okay, go to the next term, 4y. Do we have any other just plain old y's by themselves? Yes, we do. There's a negative 3y. Now, a very important thing with polynomials is to recognize that the sign in front of a polynomial, or in front of a term, stays with that term, okay? So this isn't a 3y, this is a negative 3y. You always group the sign in front of a term with the term itself. All right, so this is a negative 3y. So if I had 4y's and I subtract 3y's, I'm left with a single y, right? 4 minus 3 is 1, so we'd have 1y. Go to the next term. This is a negative 2x squared. And again, notice I'm keeping that negative in front. So if I have negative 2x squareds and I subtract 8x squareds, I've subtracted a total of 10x squareds. And last, the only other term I haven't looked at yet is this 4xy. Now, there are no other terms with both an x and a y together being multiplied, so it's its own separate term, plus 4xy. And I know it was positive because it's got a plus sign in front of it, meaning it's a positive term. All right, so that's nice and basic for all of you. Sometimes, though, part of the terms or these polynomials are in parentheses, right? Like here's a binomial minus a trinomial, right? 2 terms minus something with 3 terms. In order to combine them, you want to just get rid of the parentheses and then combine like terms, just like we did on that previous example. Now this first term, if you look in front of the parenthesis, there's nothing here. There's nothing in front of it, no number to distribute. There's no sign or anything like that. So if there's nothing in front of a set of parentheses, we can just ignore the parentheses. So I'm just going to rewrite this 7m squared plus 2m. But I'm going to write it without the parentheses, just so I know that, hey, I don't need it. There's nothing in front of it. There's no like exponent to distribute or anything outside of it. And so you don't need those parentheses. You can just basically ignore them. Now the trinomial on the right, you do have to be careful. Again, first check to see, is there an exponent or anything, which there isn't, right? There's no exponent there. But look in front. Is there something that you need to distribute? And yes, there is. This is subtraction. There's a negative sign in front of the parentheses. And so we can think of that as being a negative 1 being multiplied by every term inside the parentheses. So unlike that first binomial, I can't just ignore those parentheses. I have to distribute this negative 1 to each and every one of those terms. Now, luckily, it's just a negative 1, which isn't really a big calculation. All it's really going to do is flip the signs of each term inside the parentheses. So I'm going to rewrite this now without the parentheses because we're distributing the number in front. And when I write them down, I'm just going to change the sign of all those terms. So first, I've got this first term that's a 3m squared, which was positive, but because I'm subtracting it or because there's this negative 1 that I'm distributing, I'm going to write negative 3m squared. Now, most times students stop here. They would just put that negative with the first term and call it a day. But that is not the case. I have to distribute that negative 1 to each and every term. So this negative 6m is going to become plus 6m because we're subtracting that negative 6. In the third term, that plus 5, well, that's going to become a minus 5. It's so important to distribute that negative to each and every single term. Now we're just going to combine like terms like on that previous problem. So 7m squared minus 3m squared leaves us with 4m squareds. 2m plus 6m equals a positive 8m. And last, there's just a negative 5. There are no other constants. So negative 5 is our final term. And boom, that's simplified. I can't combine like m squareds with m's because while it's the same variable, it's not the same exponent. Those two variables represent two different quantities, right? Like if m were 7, then this would be a 7, but m squared would be 49. And clearly 7 and 49 are completely different quantities. So you cannot combine terms if their variables have different exponents. Boom, example 9. Okay, so on that previous one, we just distributed a negative sign. In this case, very familiar, you've got something out in front of a set of parentheses. This is just your classic distributive property. I distribute this term in front to every term inside the parentheses. And when you're distributing, you're using multiplication. And to multiply two terms, you multiply the like parts, meaning I'm going to multiply this coefficient with that coefficient. So 3 times 4 is 12. Then I multiply the variable with the other variable in that same term. So x to the third times x to the sixth is x to the ninth. We add the exponents because each of those x's, they have their own base. It's not like an exponent to an exponent. All right, now we go to the next term. That's 3x cubed times 2x. Well, 3 times 2 is 6, and x to the third times x, technically this is x to the first, so I have to add that into the exponents, making this x to the fourth. And finally, I'm taking 3x to the third times a negative 9. So 3 times negative 9 is negative 27. But this x to the third doesn't have any x's over here to combine with, so it just comes along for the ride. It's not going to change. It's just going to stay as that x to the third. And this right here is our simplified polynomial. How are we feeling? Yeah, you're doing good? Awesome, that's great to hear. We have 3 problems left. You got this. Oh, look at this. This looks really fun. It's a binomial times a binomial. And way back when, in Algebra 1, you may have heard a teacher say that whenever you're multiplying one binomial times another binomial, you can use something called FOIL, a mnemonic device to help you remember how to multiply these together, where that F says, first, multiply the first terms together. The first term here with the first term there, right? That's the F. The O in FOIL stands for outer, so then I multiply the outer terms. The 2x and the negative 5 are on the outside. Then the I stands for inner. These are the 2 inner terms, right in the middle. Multiply them together. The L stands for last. I multiply the last 2 terms together. So the 3 is the last term in the first binomial. The negative 5 is the last term in the second binomial. However, I don't want you to think of FOIL. I don't want you to use FOIL because it's limiting, because it only works for a binomial times a binomial, and that won't always be the case. Like example 11, that's a binomial times a trinomial. Well, that's going to be something different. So instead of thinking about foiling, here's the better way to go about this. So I've got these 2 binomials, but for now, what if I just covered up part of that first binomial? What if it was just this 3 times 4x minus 5? If I give you this problem and said, hey, multiply this together, you would know to distribute that 3 to each of those terms, right? Of course you would. But now the only difference is instead of just 1 term in front, there's 2 terms in front, right? There's this 2x as well. So I'm going to distribute the 2x times each of those terms also. And that's all FOIL truly is, right? That first outer means take this 2x times the 4x, and then take 2x times the negative 5, right? You're taking this first term, and you're just distributing it to everything in that second set of parentheses. Then take the second term, the 3, and you're also going to distribute it to every term in the second set of parentheses. So I don't want you to think of FOIL. I want you to think of distributing. And if that whatever's in front of your second set of parentheses, if there are multiple terms, all you have to do is distribute each of those terms into the second polynomial. All right, so let's go through this together. First, I'm going to take the 2x, and I'm going to distribute it to the 4x. All right, 2x times 4x is 8x squared, right? Because x times x is x squared. Then take 2x and distribute it to the negative 5, and 2x times negative 5 is negative 10x. Okay, we're doing great. I've distributed the 2x to everything so far, so now I move to the second term, which is a positive 3. So let's take 3x, I'm sorry, that's just a 3. Take 3 times 4x, which is 12x, positive 12x. Very good. And now distribute the 3 to the negative 5. Well, 3 times negative 5 is negative 15. Okay, so I've distributed everything, and we've got 4 terms in here. Your last step on these problems is to combine any like terms. For example, I've got a negative 10x and a positive 12x, so we can combine those. So we're going to have 8x squared. Now, negative 10x plus 12x gives us 2x, and then minus 15. There are no other like terms, since they all have different variables with different exponents, but that would be our final answer. So yes, it is FOIL. I'm probably going to refer to it as FOIL just to remind you what to do, but it's actually distribution. Because take a look at this next example. I've got a binomial, 2 terms, times a trinomial, times 3 terms. How the heck do we multiply this? We'll just take each term in that first polynomial, and you're going to distribute each of those terms one at a time to every term in the second polynomial. So let's start with the x. I'm going to take x times 6x squared. That'll give us 6x to the third. Now take that x times the next term in that second polynomial. So it's x times negative 4x, which gives you negative 4x squared. Now take x times the third term over there, which is 2. Well, x times 2 is just 2x. Awesome. So we distributed that x times everything in the second polynomial. Now we have to distribute the next term in the first polynomial, which in this case is not a 3, but a negative 3. Make sure you keep that negative sign with it. And I'm going to take negative 3 times each term on the right. So negative 3 times 6x squared is negative 18x squared. Then take negative 3 times the second term over there, which is a negative 4x. That gives us positive 12x. And finally, negative 3 times 2 is negative 6. Nice and easy. Now, you might have noticed how I've written these two lines below, the purple line and the green line. Why did I stagger them? And the reason being is after I multiply these out and do the distributing, we then have to combine like terms. So I kind of knew ahead of time that I was going to have some like terms to combine. So when I got this 18x squared, I knew that I already had some x squareds and that I'd combine them. So to make my life a little bit easier, whenever I multiplied my next term and I saw, oh, more x squareds, I intentionally wrote this negative 18x squared underneath the negative 4x squareds so that I know that in my next step, I'm going to combine them. And look, same thing over here, right? This 2x and the 12x, those are also like terms. So we are going to be able to combine those as well. So after you distributed everything from that first polynomial, I've now got this nice, easy addition problem. I'm just going to add up each column. First up, I've got this 6x cubed, and there are no other x cubes, so it just comes along for the ride. You just drop it down. Next, I have negative 4x squared and a negative 18x squared, which is a total of negative 22x squareds. Now the x's, 2x plus 12x is 14x. And finally, that last term, that negative 6, there are no other constants. So that is just our last constant. We drop it down there all by itself. And that's pretty much it. So you've now multiplied a binomial times a trinomial. It wasn't that bad, right? I know you're thinking, but that takes so long. Well, no, it's not really that long of a problem. And it's not that hard either. We just multiplied and added. Piece of cake. Okay, I think I've got one final problem for you. And it looks super simple. But I want to warn you, when you've got some type of polynomial with an exponent outside, in this case a 2, right? X plus 7 squared. This is not equal to x squared plus 7 squared. It's so tempting for students to just distribute it in, like I did on many problems earlier in this lesson. But we can't do that because this is not a monomial. Since there's a plus sign there, that makes this a binomial. And you can't just distribute an exponent inside those parentheses. Why not? Well, since this says that I'm taking x plus 7 and squaring it, technically, that means I'm taking one x plus 7 and I'm multiplying it by another x plus 7, right? That's what squared means. You take something times itself an additional time. And so we're really multiplying these two binomials together. So that's what I want you to remember, because you're definitely going to see a problem like this on a test and different assessments on the ACT, blah, 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 all that stuff. And you need to know, okay, I'm actually multiplying two binomials. I'm not distributing that in. So now I have x plus 7 times x plus 7. I'm going to distribute the x times each of those terms. That gives me x squared plus 7x. Then I will distribute the 7 to each of those other terms. Well, 7 times x is another 7x. And 7 times 7 is 49. Finally, I've got these like terms in the middle. Those are both just x's. So our final solution would be x squared plus 14x plus 49. So this is the correct simplified version of x plus 7 squared. Whereas if we did just distribute the 2, we would get x squared plus 7 squared, which is 49. And you can see right there, we'd be missing out on this middle term, that 14x. So that'll be equal to something completely different, which we don't want. So make sure if you see a binomial or trinomial or anything bigger squared or to the third or fourth power, that you don't just distribute that exponent in. That is only for monomials. Anyway, I hope this was a fun little refresher for you, everybody. I know I had a great time, and it should have been nice and simple review. Anyways, I want you to go ahead right now to Delta Math and practice, practice, practice. Make sure you have all these skills down pat before our next lesson. All right, have an awesome day, everybody. I'll talk to you later.